So what do we got? We got our function f is concave up on two intervals. Actually, it's concave up on the interval that goes from negative infinity to negative 2 minus root 2, but also on the interval that goes from negative 2 plus root 2 to infinity. So that's where it's concave up, and then it's concave down in between. So on the interval that goes from negative 2 minus root 2 to negative 2 plus root 2. And then we have two inflection points, which were a bit nasty to write down, but we got them. So what were they? Well, the first one had an x-coordinate of negative 2 minus root 2, and then the y-coordinate was negative 2 minus root 2 squared times e to the negative 2 minus root 2. So that was one of them. And the other one, which I'll write below, we had negative 2 plus root 2. And the y-coordinate was negative 2 minus root 2, or pardon me, negative 2 plus root 2 squared times e to the negative 2 plus root 2. So that is your final answer for that example. Has all the information summarized. All right, so our last one now is the one that had the natural log. So we've got our function h defined by h of x is equal to x squared times the natural log of x. So we've got a product. So when we go to find our derivative, our first derivative, we'll use the product rule. So derivative of x squared is 2x, and we multiply it by the natural log of x. Then for the other term, we're going to take x squared and multiply it by the derivative of the natural log of x, which is 1 over x. Okay, so what does h prime of x work out to be if you clean it up? Well, x squared times 1 over x is just 1 over x, so why don't we write this as 2x times the natural log of x plus x. And then now we're ready to take our second derivative. So differentiate again. So your h double prime of x, we'll do the product rule for the first term. This is a product. First factor is 2x, and the second factor is natural log of x. So the derivative of that is going to be, well, 2 times the natural log of x plus 2x times the derivative of natural log of x, which is 1 over x. And then when we differentiate the last term, the x is just going to become a 1, so we have plus 1. All right, so what do we get? 2 times the natural log of x. Here we've got 2x divided by x. The x's will cancel, we'll just get 2. So we've got, this is really just 2. We add 1, so we get 2 ln x plus 3. All right, so when is h prime of x going to be 0? That's the first question. Or h double prime of x, I mean. H double prime of x is going to be 0. Well, let's solve the equation. 2 natural log of x plus 3 is equal to 0. When's that going to be true? Well, when 2 times the natural log of x is equal to negative 3. Or, in other words, the natural log of x is equal to negative 3 over 2. And now we can use cancellation properties to solve for x. Just raise e to the power of both sides, and you'll get x is equal to e to the negative 3 halves. So that is our important value. Again, not the nicest value to work with, unfortunately, but that's just the nature of math sometimes. Some of the problems that we've looked at, the numbers have worked out very nicely, but in practice that may not happen. So we have to be prepared to work with some less than convenient values sometimes. Okay, what about when h double prime of x is undefined? I'll probably sneak that in down here to save some space. So h double prime of x is undefined when? Well, h double prime of x is 2 times the natural log of x plus 3. Well, I mean, this is not defined for negative x, right? So what are we going to do? List every single negative value? Well, you couldn't do it. And really, when we look for places where h double prime of x is undefined, what we really mean is we're looking for singularities. We're looking for isolated points of where the function might not be defined at a single point within an interval, or maybe it's discontinuous, or pardon me, maybe the original function is discontinuous there. But we're not really interested in the fact that h double prime of x is always undefined for every negative value, right? And another way to think about that is if you go back up to the original function, what's the definition of the original function? H of x is equal to x squared times the natural log of x. So this function is not even defined for negative values of x. Why don't we make a note of that and say up here, note, the domain of h is equal to positive numbers, the set of all positive numbers. You can't plug in 0 to the natural log, nor can you plug in a negative number. The x squared is no problem. That'll be defined everywhere. So the only concern is negative numbers or 0. So the domain of our function h is all positive numbers. So are there any numbers within that interval where h double prime of x is undefined? No. Because this is defined for all positive numbers. So this is going to never happen. So it's important to consider what your domain is, what the domain of the function is as well. So okay, so that's it for our values that we care about. E to the negative 3/2 is the only value that we're going to put in our table. So let's draw the table up here. We've got the second derivative table. Well, we're going to have, as usual, one row for each of h double prime and h. Then e to the negative 3/2, that was our value here that we found, e to the negative 3/2. And now we're going to need to pick a sample point here and here. And again, we've got the value that we have here. You have to be careful. We can't we can't be careless here. We have to pay attention to what value this is and make sure that what we choose here is actually smaller than this value, and what we choose here is actually larger than this value. So here is the way I would suggest to do that. Okay, this is e to the negative 3/2. What does the graph of e to the x look like? Particularly on the negative half of the x-axis. It looks something like this, right? Where that is 1 on the y-axis. So this is the graph of the function e to the x. Okay, I just want to be clear what we're actually graphing here. And then it has a horizontal asymptote along the x-axis. As the x values get very, very far to the left, the y values of the points in this curve just come in for a landing on the x-axis, but never actually touch it. It's a horizontal asymptote on the x-axis. So what we have here, e to the negative 3/2, well, that's really the y value of the point on the graph here. If I plot negative 3/2 here. So what is my point? What's the point of this? Well, we want to pick a value here that is less than e to the negative 3/2. So what happens if I just take negative 3/2 and replace it with a value that's further to the left along the x-axis? Well, the y values of these points are getting smaller, right? They're decreasing and getting closer to the x-axis. So if I were to pick something like negative 2 there, that's a value that's further to the left on the x-axis than negative 3/2 is. And the y-coordinate is actually smaller than the y-coordinate at this point. So what's the significance of that? Well, e to the negative 2 is less than e to the negative 3/2. Right? Negative 3/2 is like negative 1.5. So this is negative 1.5. If I go a little bit further to negative 2, then this is actually going to be further to the left on the x-axis, and the y-coordinates are going down, so that's why you know the e to the negative 2 is actually smaller than e to the negative 3/2. So why don't we put e to the negative 2 here. Now if I want a value that's larger than e to the negative 3 halves, well, I can just move a little bit in this direction because then the y values are going to get higher, which means that if I choose an exponent that's a little bit larger than negative 3 halves, and by larger I mean moves in this direction, then the e to that exponent will be larger than e to the negative 3 halves. So what I mean by that is let's put negative 1. Let's say that's right here. It's not perfectly to scale, but that's okay. All right, well then the idea is that since the y value on the graph above this point is higher than the y value on the graph above this point, e to the negative 3 halves is less than e to the negative 1. Because the y coordinate on this point is higher and the y coordinate of this point is lower. So anyways, the upshot of this is e to the negative 1 will work as a point that you can plug in here. So that's how we can get that. Okay, well let's actually plug them in then. Okay, let's actually plug those values in and figure out the sign of h double prime so we can get the concavity. So this graph was just some side observations that we could use to justify our choice of sample points here. Okay, well, let's plug these in. So let me clean this up so I don't want the work to crash into my other work. So let's plug those points in down here. H double prime of e to the negative 2. Let's plug that in, and we can figure out if this is positive or negative. Well, h double prime of e to the negative 2, we're going to plug e to the negative 2 in here. So we're going to get 2 times the natural log of e to the negative 2 plus 3. All right, and then, well, what happens? Natural log of e to the negative 2, this just works out to be negative 2 by cancellation properties. The e and the natural log cancel, and this whole factor here just resolves into being negative 2. So we get 2 to the negative 2 plus 3, which is really just negative 4 plus 3, which is negative 1, which is less than 0. Okay, so that means we have a negative here. It means our function is concave down. Okay, and what's next? Well, we've got h double prime of e to the negative 1, because that was our sample point up here that we're plugging into h double prime now. So h double prime of e to the negative 1, we're going to have 2 times the natural log of e to the negative 1 plus 3. So this is just going to turn into negative 1 now, for the same reason that this turned into negative 2. So we'll have 2 times negative 1 plus 3. That's going to be negative 2 plus 3, which is positive 1, which is greater than 0. So that means this is positive here, and that means we're concave up. All right, so good, we've got our concavity. Do we have any inflection points? Absolutely. We have an inflection point right here, because e to the negative 3 halves, that is a positive number, so it's in the domain of the function h. It's a positive number because e to the anything is positive. Remember, this is the graph of e to the x. It's always above the x-axis. So that means this is an inflection point. Let's get its y-coordinate, and then we're ready to summarize our answer. So finally, let's plug in e to the negative 3 halves to our function. Right? Again, not the nicest value, but it's what we have, so we have no choice. So we're going to plug that into the original function h. So we're going to get e to the negative 3 halves squared times the natural log of e to the negative 3 halves. Okay, so well, this will just, the ln and the e will cancel, and this whole factor will turn into negative 3 halves. And then here we've got e to the negative 3 halves, and then the whole thing is squared. Remember, when you have nested exponents, what do? You multiply them. So we're going to have negative 3 halves times 2. That's just going to turn into negative 3. So really what we're going to get is just e to the negative 3 times negative 3 halves, which really, that cleans up quite nicely. If you just write that, we can write that as negative 3 over 2 e cubed. That's really what it equals. So that wasn't too bad. So that's going to be the y-coordinate of our inflection point, and it looks like we've got enough room that we can summarize everything at the bottom of this page without having to start a new page. So let's do that now. So h is concave down on the interval that goes from negative infinity to e to the negative 3/2, and h is concave up on the interval e to the negative 3/2 to infinity. And then for inflection point, what do we got? We have the point that has an x-coordinate of e to the negative 3/2, and the y-coordinate was negative 3 over 2e cubed. Okay, so that is our inflection point, and that is everything that we were asked for. So this problem was a little bit tricky as well, because there was the details were a little bit maybe more involved than they sometimes are. Right, so we've done some simpler examples, and we've also done a few more challenging ones as well. But this is what it means to investigate the concavity of a function. You're looking for all the places where it's concave up, looking for all the places where it's concave down, and then you also want to find any inflection points, which, remember, the inflection points are the places where the concavity changes. They're points on the graph where the concavity changes.